We'd like to thank Speakly for supporting PBS. When we think of an exotic state of matter, we tend to think of the really weird things that matter can do in extreme circumstances. Like how at very high temperatures we get the plasma that the sun is made of, or at extreme densities we get the nuclear matter of neutron stars, or in extreme cold we can have superconductors and superfluids. But there's one state of matter that's not solid, liquid or gas, but is also not confined to extreme or rare environments. In fact, there are planets in our solar system completely covered with this stuff, and you've often been the beneficiary of the powers of this state of matter without even knowing it. I'm sure you know how states of matter work. Heat a block of ice and it melts into liquid water, keep heating and it boils into gas, water vapor. We've been over this stuff before. If you watched our episode on states of matter, you'll know it's a bit more complicated than this. For example, it's not just temperature that determines the state of matter, it's also pressure. The reason solids melt and liquids boil is that rising heat energy allows bonds between atoms and molecules to break. But high pressure helps to keep particles together, so it takes more heat energy to break bonds. That's why water remains a liquid at 400 degrees Celsius near hydrothermal vents on the ocean floor, while it boils at only 68 Celsius on top of Mount Everest. The relationship between temperature and pressure and phase is mapped on a phase diagram. Now, maps tend to be covered by nation states or states of the Union, but this map has states of matter. And these also have boundaries, the crossing of which means changing state, say by increasing temperature through solid to liquid to gas. At these melting and boiling boundaries, the material is momentarily a mix of both states. But there are some surprises on this map too. For example, at lower pressure, there's a boundary where increasing temperature takes you directly from solid to gas. We call that sublimation. And there's this so-called triple point, where all three states of matter exist simultaneously. From the triple point, if we increase both temperature and pressure in the right proportions, we follow the phase transition boundary between liquid and gas. If we're careful, our fluid remains in an equilibrium state, simultaneously boiling and condensing. But eventually, we reach this spot, where the boundary appears to end. It's almost like the map gives out, as though our explorer experimentalists haven't travelled that far across the realms of pressure and temperature. But that's not the case. This endpoint of the liquid-gas boundary is called the critical point, and it's very real. And beyond it is an entirely new state of matter, a here be dragons of the phase diagram. This is a land with no boundaries, a sort of no man's land where liquids can skirt around the phase boundary and become gases without ever boiling. In that region, matter becomes a sort of hybrid between liquid and gas called a supercritical fluid, sharing the properties of both. But this is a genuine unique state of matter that can do things not possible for either liquids or gases. What does it even look like to transition between states without ever crossing a phase transition boundary, or to be a combination of liquid and gas? Well, I'm going to show you. But first, to understand what we're going to see, we need to remind ourselves of the fundamental properties defining liquids and gases. To start with, both are fluids. They flow. They can't hold a rigid structure like solids can, rather they take on the shape of their container. A key property differentiating liquids and gases is their inclination to change their own volume or density. Liquids, for example, are remarkably difficult to compress in volume by the application of external pressure. That enables their use in things like hydraulic presses, where they can be used to exert enormous outward pressures. We say that liquids are incompressible. In some cases, they're less compressible than their own solids. And the volume of liquids doesn't change even in the absence of external pressure. The particles of a liquid are loosely bound to each other, which manifests as a surface tension and results in liquids having a distinct surface. That pulls liquids into spherical blobs in freefall or in the absence of gravity, while under gravity they take on the shape of the bottom of their container. While pressure doesn't influence liquid volume, temperature does. Liquids expand with heat. Gases, on the other hand, always expand to occupy the entirety of their container, and are also relatively easy to compress by exerting pressure. Gas particles zip around without significantly interacting with each other. They keep moving until they hit a container wall. Those impacts exert a pressure on the container. Expand the container and the gas will expand, but it'll take longer for each particle to travel between the walls, so pressure drops. Vice versa if you shrink the container. Increase temperature and the gas particles move faster, hit harder, again increasing the pressure. For a so-called ideal gas, which has no interparticle forces, its behaviour can be described by a simple relationship between pressure, temperature and volume, given by the ideal gas law. PV equals NKT. Okay, that's about enough blah blah pressure blah blah. We now know what we need to know to take the journey to that strange new land of the phase diagram. Let's see what it looks like for a liquid to pass into the supercritical phase. Now we're going to do that with the help of Nigel Braun of the Nile Red and Nile Blue YouTube channels. I suggest you watch the entire video yourself, but with Nigel's kind permission, we'll show you the highlights. This is a pressure chamber containing dry ice, carbon dioxide in solid form. That ice was presumably created below the 194.7 Kelvin freezing point of CO2 at atmospheric pressure. Now at room temperature, it begins to sublimate directly into a gas. At atmospheric pressure, liquid CO2 can't exist. But in the small volume of this chamber, sublimation causes pressure to rise, taking us into the realm of the phase diagram where liquid CO2 is possible. That liquid fills the bottom of the chamber, while the top of the chamber is mostly filled with CO2 gas at a much lower density. To reach supercriticality, we need to get to this part of the diagram, so both pressure and temperature need to increase. Conveniently enough, it's possible to get there just by adding heat, and Nigel does that with a hairdryer. As temperature rises, the pressure of the gas increases a proportional amount, but this temperature is also causing thermal expansion in the liquid, which reduces the volume of the gas, which further increases the pressure all around. At first, we might think this pressure has no effect because liquids are incompressible, but look at the phase diagram. At higher pressures, the boiling point of CO2 increases. This means all this pressure makes it harder and harder for the liquid to evaporate. So now we have a sort of feedback loop where the liquid wants to transition into a gas, but the more it tries to, the less it's allowed to. We remain stuck following the transition boundary, upwards in temperature and pressure, trapped in our state by thermodynamics. But we're approaching our strange new region of the phase diagram where the rules are going to change. But before we get there, let's talk about density. Since the gas is being compressed, but its mass is not changing by much, its density must increase. Meanwhile, the liquid is expanding in volume, so its density drops. Eventually, the density of the gas and the liquid become the same. At that point, microscopic droplets of the remaining liquid are free to flow and swirl through the gas phase to diffuse. We're now at the critical point. And then all of the CO2 goes supercritical and it appears to vanish. It becomes perfectly transparent. From its visual appearance, the supercritical CO2 could easily be a gas. And really, it is a lot like a gas. It fills its container and it's compressible and it doesn't have the surface tension of a liquid. The viscosity of supercritical fluids is extremely low, like gases, so they flow and diffuse more like a gas than a liquid. But this has the density of a liquid, and that leads to behaviours not seen in gases, which I'll come back to. The high density of a supercritical fluid means that its particles do interact with each other, unlike an ideal gas. That means the supercritical equation of state is much more complex than the ideal gas law. To demonstrate the hybrid nature of this stuff, Nigel put some silica beads in the chamber. On shaking the chamber, the beads move only slightly, like they're underneath a liquid. But now, with only gas in the chamber, they rattle around as expected. And finally, let's reverse this. When ice is applied to the chamber, temperature drops and CO2 liquid rapidly condenses from the supercritical phase. On the other hand, if the chamber is opened, then the pressure drops. and the supercritical fluid transforms straight into a gas instead of a liquid. Perhaps the most useful property of the supercritical fluid is its ability to dissolve stuff. Due to its high density compared to a gas, it has more atoms or molecules to bond to the dissolved substance. But it still moves like a gas, so it can flow and diffuse into places that liquids can't access. One very familiar application of this super solvent is decaffeinated coffee. If you put coffee beans into a bath of supercritical CO2, the fluid will diffuse into the beans like a gas and bond with the naturally soluble caffeine and then diffuse back out again. The now caffeinated CO2 can be brought back into gas form, leaving a decaffeinated bean and a fine powder of caffeine molecules, I guess for the energy drink that you need after your decaffeinated coffee didn't work. Here's another one. The lowest density solids in the universe, aerogels, are made the same way. A gel is a molecular scaffold full of water. If you try to dry out the gel, it shrinks. That's because when water evaporates from the surface, capillary action draws water from the interior, and that causes an inward tension on the scaffold, and so it collapses. But if you put the gel in a supercritical CO2 bath, the fluid will replace the water, and then you can turn the CO2 back into its low-density gas phase, leaving the gel lattice intact and full of air. These aerogels have a ton of applications, but by far the most interesting is to send them into outer space to catch cosmic dust, like in NASA's Stardust mission. What else? You ever had something dry cleaned? Again, supercritical CO2 is used to dissolve stuff, in this case whatever's making your clothes filthy, but without the risk of getting your precious, hand-dyed silk pajamas wet with actual water. There are countless applications of supercritical fluids even beyond the many applications as a solvent. For example, they're increasingly important in material science for their ability to deposit dissolved elements for growing nanoscale particles and layers. They're great at moving heat energy around due to their high density and correspondingly high heat capacity. So we see more and more application as the working fluids in power plants and heat pumps and as refrigerants. Industrial applications often use supercritical carbon dioxide, but supercritical hydrocarbons also see a lot of use, and supercritical water is important also. It's good for all those things you want water for, electrolysis, hydrolysis, oxidation, but when you want to avoid actual wetness, or you need the stuff to flow and diffuse like a gas. Okay, good for us. We discovered supercritical fluids, and we can now sip our decaf lattes in our nicely dry cleaned silk pajamas. But nature knew about this state of matter long before we did. Unlike other exotic states, supercritical fluids can be found on Earth, or rather in the Earth. Water circulating deep beneath the ground in geothermally active areas can reach the high temperatures and pressures needed for a supercritical state, and even, albeit rarely, emerge in that state in hydrothermal vents on the ocean floor. This stuff is rare on Earth, but if you lived on Venus, you wouldn't think of the supercritical fluid as a fringe state of matter at all. The Venusian atmosphere is almost entirely carbon dioxide, creating a greenhouse effect that heats the surface to more than 700 Kelvin. Combined with the extreme atmospheric pressure, this puts CO2 within a few kilometers of the surface, well beyond the supercritical point. We often think of Venus as a rocky planet, but it's also fair to think of it as an ocean world, an ocean of supercritical fluid that I don't recommend you try swimming in. Jupiter, Saturn, and probably the other gas giants are also supercritical ocean worlds in a way. They have solid cores of rock and ice, and in the case of Jupiter and Saturn, those are surrounded by solid metallic hydrogen, but then we have a thick layer of supercritical fluid, mostly hydrogen. All of that is buried beneath extremely thick atmospheres of gas phase, mostly hydrogen, but the supercritical layer is an integral part of the structure of the biggest planets in our solar system. So let's review all the states of matter. Solids, liquids, gases, plasmas, supercritical fluids, Bose-Einstein condensates and the resulting superconductors and superfluids, nuclear matter of various types, photonic matter, various spin-based states from ferromagnets to quantum spin liquids to time crystals. Come to think of it, let's not review all the states of matter, because I'm starting to think that there may be no end to the weird ways that matter can be. Now, many of these are total edge cases, but some, like supercritical fluids, are incredibly and increasingly useful. And while this stuff is rare on this mostly wet and gassy rock, supercritical fluids are surprisingly abundant in other parts of space-time. We'd like to thank Speakly for supporting PBS. If time travel were invented and you thought, great, now I can go back to the 1920s and debate interpretations of quantum mechanics with Einstein and Schrödinger, well, you'd need to learn German, unless you already know it. But even in this current time period, if you've wanted to learn another language, then I'd like to introduce you to Speakly. Offering 8 different languages to choose from, Speakly was created by 2 polyglots who both speak 7 languages. They researched thousands of language learners and created a unique method that teaches words and sentences based on their relevance in real-life situations. This means that you don't learn anything that you actually can't use to speak the language. Available on both web and mobile platforms, you'll learn new vocabulary with speaking exercises, writing exercises, listening comprehension exercises, and even music recommendations in the language that you're learning so you don't get bored. There's a link in the description to learn more. Before we get to comments, I wanted to let you know that there will be an end-of-year AMA next Monday at 4 PM Eastern Standard Time on the channel. We'll post more information on the community tab, and we look forward to hearing your questions. This will be the last content before we take a holiday break. Today, we're doing comment responses for the last 2 episodes, the one on quasi-particles, and the one where we talked about the recent detection of neutrinos coming from a supermassive black hole. Let's start with the quasi-particles. Some Kid and Cybernatural ask whether quasi-particles could be used to explain dark matter. Well, the answer is unfortunately almost certainly no. Quasi-particles require some sort of non-elementary field to exist in. In other words, they exist in fields that arise from a volume being filled with matter. Dark matter suffuses the near vacuum of space, where we mostly just have the elementary quantum fields. Excitations in those fields are proper elementary particles, not quasi-particles. Amorphant points out that we didn't mention magnetic monopoles as an example of quasi-particles. Well, the reason that we didn't is that I didn't know that these things had been created as quasi-particles, so thanks for the heads up. Actual magnetic monopoles, if they really exist, would be elementary particles, and we've done an episode on these before, but it turns out that they can also be created as quasi-particles by separating the poles of regular dipole magnetic fields, for example, by careful manipulation of spins in a crystal lattice. Check out Felix Flicker's Royal Institute talk for an example, link below. Dr. Lisa Schumacher of the Ice Cube collaboration dropped into the comments to say hi and to let us know that the updated Northern Sky neutrino map is available. I put the link in the description. So it's crazy to me that an observatory at the South Pole observes the Northern Hemisphere sky because it needs the Earth to be in the way. Anyway, thanks for stopping by, Dr. Schumacher, and thanks for all the hard work of you and your team. GNGR11 asked whether it's possible to detect and map the cosmic neutrino background, like what was done with the cosmic microwave background. Well, first, the cosmic neutrino background refers to the neutrinos that were created at around 1 second after the Big Bang, when the density of the universe became low enough for neutrinos to travel freely. These neutrinos would now have energies 10 billion times smaller than regular neutrinos, say from the Sun. That makes them way harder to detect, and we've never positively identified one. There are experiments currently being built to try to detect these, but those experiments won't be able to measure the direction these neutrinos came from. Making an actual map sounds extraordinarily difficult and may not be possible. Some random guy asks, what would our night sky look like if our galactic center had a quasar? Well, that's a great question, and I don't know. Well, I do know now because I figured it out. Quasars, or active galactic nuclei, glow from the heat energy of matter being ripped to shreds as it spirals towards a supermassive black hole. According to Arthur Eddington, there's a maximum brightness for an object like this determined by the maximum amount of fuel that you can pour in before the outgoing radiation stalls the fuel supply. The limit for the Milky Way's black hole is around 100 billion times brighter than the Sun. But you factor in the relative distance of the center of the Milky Way, and you get that a Milky Way quasar shining at the Eddington limit would be about 3 times brighter on our sky compared to our Sun. It would also have a much harder spectrum, so a lot more nasty UV light, not to mention X-rays and gamma rays, which may wreak havoc on the ozone layer. Now, not all active galaxies glow at the maximum, and there are also regions of such galaxies that are shielded from the inner quasar by a thick wall of dust surrounding the whirlpool, so the number I gave you is a worst case scenario. Still, probably not something that we should be hoping for, and happily it's also not something that can happen, at least in the next few billion years. Harmony Smurf and Wexsource echo my warning about seeing flashes in your eye. It is almost certainly not a neutrino. Go and see a doctor. Apparently, migraine auras and vitreous detachment are a common cause of flashes. A retinal detachment is a much rarer possibility, but still not as rare as seeing Cherenkov radiation from neutrinos. Still, this would make a pretty awesome house episode, right? And I would be willing to do a cameo. I've always wanted to be a consulting astrophysicist at a hospital. I'd finally feel like a real doctor.